AI's next bottleneck is moving data and managing heat, not simply adding more compute. This week's research points to a deeper shift, from 3D chiplets that co-optimize wiring and thermal behavior, to open models challenging the cost structure around frontier labs like OpenAI and Anthropic, to Huawei's bus architecture that radically reduces memory transport overhead. Together, these results suggest the next AI infrastructure cycle will be decided by bandwidth, locality, and system-level control as much as model quality. We'll unpack the performance claims, the economics, and the caveats behind them. Let's explore the first paper, Chiplet 3D Pin and Thermal-Aware 3D Chiplet Floor Planning via Convolution Embedded MILP. Chiplet 3D from Shuo Ren and colleagues is a 2-die 3D chiplet floor planner that addresses a central limitation of stacked designs, heat trapped between active dies, as seen in products such as AMD 3D V-Cache, TSMC SoIC, and Intel Foveros. Its first novelty is pin-aware half-perimeter wire length. Instead of connecting block centers, the MILP pre-computes exact pin coordinates under 4 rotations and 2 flips, allowing orientation choices that align real terminals. Its second novelty is a coarse convolutional thermal field embedded directly in the MILP. Calibrated point spread kernels approximate lateral and vertical heat conduction on a grid, while a 2-stage flow first creates a thermal skeleton and then uses dynamic thermal elasticity to recover shorter wiring without violating thermal constraints. Evaluated on the ICA 24 AT-Place benchmarks, with final temperatures verified by Golden 3D ice simulations, Chiplet 3D reduces wire length by 39% to 43% on average and by up to 62% in the best case. It lowers peak temperature by up to 45.9 degrees C and thermal non-uniformity by up to 56% versus state-of-the-art baselines. Across 10 cases, it achieves the lowest bottom die peak temperature in 8 cases and the best thermal uniformity in 9, while producing the shortest average pin-aware wire length. The results show that exact pin alignment and solver-integrated thermal spreading create a stronger wire length temperature Pareto frontier than center-based or post-placement thermal estimation. Let's explore the second paper, Memory Scarcity, Open Models, and the Restructuring of the AI Industry, 2026-203-0205. A quantitative scenario analysis of inference economics, training cost divergence, and infrastructure solvency. Satoshi Matsuoka's scenario analysis argues that AI infrastructure from 2026 to 2030 will be reorganized by memory economics rather than compute alone. It models decode cost in dollars per petabyte of delivered HBM bandwidth and identifies a depreciation conveyor. Incumbents with sunk fleets retain a structural advantage over entrants, reaching 3.2 times in 2026 because new capacity absorbs the HBM premium while older hardware moves to marginal cost. Open-weight systems such as GLM 5.2 with 744B total and 40B active parameters, combined with TurboQuant's near Shannon limit KV cache compression, MOE sparsity, quantization, routing, and local runtime such as Dwarf Star 4 push routine workloads toward commodity pricing. The paper therefore separates a luxury tier frontier models from OpenAI and Anthropic from a mass tier increasingly served by open models and infrastructure controlled by firms such as Meta and xAI. Its solvency corridor requires approximately 2 times annual token demand growth for 4 years, when efficiency improves 30% per year. Slowing efficiency gains to 15% lowers the threshold to about 1.6 times. Meanwhile, frontier training costs could reach $18B by 2030, while reinforcement learning and distillation on open bases approach $5 million. The analysis flags OpenAI's Stargate commitments, NVIDIA's financing exposure, Metacompute, and xAI's Colossus lease to Anthropic as examples of balance sheet concentration. Its central greenfield entry estimate is 25% success, 34% mediocrity, and 41% loss, implying that staged investment, secured HBM, anchor demand, and 2027 timing matter more than custom silicon alone. Let's explore the third paper, OpenURMA, a clean room open implementation of the Unified Bus Protocol. OpenURMA, from Boji Lee at PineAI, is the first clean room open implementation of Huawei's Unified Bus Protocol, developed to address RDMA's Q-pair over PCIe bottleneck. Unlike ROS-F2, which maintains per application, per remote endpoint state, and requires repeated PCIe crossings, UB separates application endpoints called jetties from per-host TP channels, reducing state growth from ONM to ON plus M, places the controller on the CPU's on-chip bus, and exposes native load, store access, with 4 opt-in ordering axes. The implementation uses a shared OpenClick NP description across synthesizable RTL on an Alveo U50, a cycle-accurate 2-node System C simulator, and a Gem 5 full system scaffold, each compared with matched OpenROSI. For a 64-byte remote fetch, UB's load store path reaches 500 ns end-to-end versus 2,186 ns for ROSI, a 437-fold reduction, while sustaining 280-fold higher work request throughput. At 1,024 local and 1,024 remote endpoints, OpenURMA uses 110.6 kilobytes of connection state versus 536.9 megabytes for ROSI, a 4,855-fold reduction, and the RTL closes at 322 MHz, using 14.1% of the U50's LUT budget. The study also reports 2-fold higher YCSBA throughput, selective acknowledgements that outperform go back N under loss, and congestion control reaching 96% utilization versus 62.5% for DCQCN. These are modeled and FPGA post-route results rather than measurements on physical UB silicon. Huawei's Ascend 950 is closed, while NVIDIA's ConnectX 7 data calibrates the ROSI baseline. The paper states that its code and manuscript were produced with Pine Copilot and Claude Code. That's a wrap on today's AI paper highlights. Thanks for watching.